Hey everyone, I am Dr. Vipul Pandey and I am going to start a new lecture series, Problems and Solutions in Quantum Mechanics, which will be useful for students preparing for JAM, NET, GATE, JEST or any other exams like TIFR For or IISc or like that, right? So we will start from the very beginning of the quantum mechanics and go up to this before the relativistic quantum mechanics. And we will see at the end whether it will be feasible to discuss some of the problems related to relativistic quantum mechanics also. Right? So let us start with it. So we will take one by one some of the problems today, and then we will keep on discussing on topics related to these exams. Right? So let me take the first problem. So I am taking a simple problem which will be useful for you. So it says, question number 1 is there, which says that classically wave exhibits interference pattern, right? Pattern, right, that we all know about, but particles do not, right? When two non-interacting streams of particle combine, in the same region of space, right, their intensities add. This is what usually happens. Right, intensity is adding. Now, whereas when waves combine, their amplitudes add. Their amplitude add but not intensities. Right? So it is asked that whether this statement is true or false. And B is false, right? So let us analyze this experiment statement first. What does it say? That classically means when you talk about the classically, so you are taking out of the Planck's region, right? From where the quantum behavior starts, right? So classically, waves exhibit interference pattern and particles do not. Obviously, that is true. So when two non-interacting system of particles combine in the same region of space, their intensity adds. We know already. This is from the Young's double slit experiment or like that. So we already know about this behavior that their intensities add. Whereas when waves combine, right, So stream of particle, the intensity at, where intensity is obviously you know that it is square of the proportional to square of the amplitude. Whereas when waves combine, their amplitude are, right, but not intensities, right. So that is true from the Huygens principle also, that when waves are combining, their amplitude will add, whereas their intensity doesn't add in the case of waves, and in case of particle, their intensity add, and that is so. The statement is true. Remember that. This is simple result, right? So in case of particle only, always the intensity will be added, whereas in the case of wave, amplitudes are added, right? So this thing you must remember always. Now we will go to another problem, question number 2, which I am taking from here, from my note. So let us take this problem. So consider two wave functions. Okay, so let me remove this first, then I will start with problem number 2. Then the board is obviously of a sort of. So let us go to the question number 2, which says that consider two wave functions. Right? Psi1 xy sorry yt, not xt, yt as 5y cos 70 and psi2 yt as minus 5y cos 90. Right? So these two are there, where y and t are obviously displacement are in meters and second respectively. So it represents the amplitude of meters and seconds, second respectively. Now what is asked? The superposition psi xt, psi yt of the two wave function will be. So let us calculate. Ask that what is superposition? Psi yt of two waves will be. So this is asked what will be it, right? So let us find the superposition. As no information has been given about whether they are interacting with each other or whatsoever. So what you will do when you are calculating the superposition, you will simply add them. So psi at yt is nothing but psi1 yt plus psi2 yt. Right? So just put it like that, the expression which is given as 5y cos 70 minus 5y cos 90. Right? Now take 5y as common and this cos 70 minus cos 90. When you simplify, this is a formula of what? Cos A minus B minus cos A plus B, which is what? 2 sin A sin B. So you write it cos A minus B, cos 8 minus 1t, right? A minus B. As it is 7 is 8 minus 1 and 9 is 8 plus 1. Cos 8 plus 1t. Right? So it can be simply written as 5y multiplied by 2 sine so cos a minus b. So a is here this and cos a plus b. Right? We are taking this. So it will be 2 sine t sine a t. Right? It can be of any order. It is because cos is always positive. In whether cos theta is negative, right? So cos of minus theta is cos theta. So it will be giving you 10y sin t sin 8t. So this is another problem. You see how we can calculate a superposition when no information regarding their overlap or anything in relation between the two waves is given, right? So now we will see another problem. One more. These are simple problems based on what we call modern physics, which is the beginning of quantum mechanics. Now let us take another problem, question number 3. Question number 3 says the de Broglie wavelength of electron moving with a speed. So what is the de Broglie wavelength of an electron? Wavelength of an electron moving with a speed so to the power 5 meter per second, right? So this is given. Supply constant is given as h equals to 6.63 to the power minus 34 Joule second, right? Joule second. So let us calculate the de Broglie wavelength. You know it's a very simple problem. Sometimes it can be asked. So lambda, which is called h upon p. This simple formula. Lambda, the wavelength, h and p. So wave, so particle having the momentum will also show the wave nature. This is what the de Broglie. So matter shows the wave nature. That is what the de Broglie's hypothesis says, right? So matter, which is so here, matter is any particle with mass and moving with finite velocity, will show the wave nature. It has the wavelength, right? So this, so it's implying lambda is what? H is 6.63 into 10 to the power minus 34 divided by P is what? Electron's mass is 9.1 into 10 to the power minus 31, right? kg. We are all taking, we are taking the SI units only, and this is 10 to the power 5 meter per second. Right? Now let's simplify it to calculate the lambda. So it is how much? Ten to the power minus 34 plus 31 minus 5 divided by 9.1. Right? So when you simplify it, you will get it a little higher because this is 9, it is close to 10, so it will just increase it. It will be somewhere like 6.8 or 9. You need to verify it. So it is close to that. Into 10 to the power minus 30, this is minus 3 minus 5, 10 to the power minus 8. right? Meter, right? Just change it to nanometer, which will be 69 nanometer, right? Because 1 nanometer is 10 to the power minus 9 meter. So when you divide by 10 to the power 9, you simply multiply it by 10. So this is the wavelength of the electron. So this is a simple problem. Now let us go to another problem. So we will try to understand more number of problems basically, as we are today we are discussing very simple problems. Let us take down the problem, question number 4. Now it says when an incident light, these are mostly elementary basic problems. When an incident light of energy h nu falls on a metal of work function omega. W like that, right? And the threshold frequency nu. Nu naught, right? Then electron emitted with kinetic energy, or then the kinetic energy of electron will be emitted electron, because now you know this is nothing but what we call this experiment, photoelectric effect, right? So when a light of a certain frequency fall on a metal surface, and then depending upon the work function of metal surface and frequency of the light, the electrons will be emitted, right? So let us assume, and that doesn't depends on the intensity of the light, but rather depend on the energy of the photon or energy of the light which is falling. So let us take a solution here. So use a simple conservation law. So h nu is the total energy of the light which is falling on the surface, which is equals to h nu naught, which is nothing but the work function or the basically binding energy of the electron or the surface, right? Which is minimum energy required to bring the electron out of the surface, plus kinetic energy, right? This is simple energy conservation. The kinetic energy is what? H nu minus H nu naught, where H nu naught is work function. So this is the result we all know. Kinetic energy is, right? This is simple photo relation of for the photoelectric effect. For kinetic energy of the electron which is emitted from the surface, and the this frequency or energy of the light which is falling on the surface, and the work function of the surface. Right? Now let us go to another problem, which is the last problem of today's lecture. Right? So this Question number 5. Let us take this. So it says the pair which must obey Heisenberg's uncertainty principle are. The pairs which must obey the Heisenberg uncertainty principle are. There are some pairs are given. So these are the pairs. Let me solution write here. What are the pairs we have? So quantities which are canonically conjugate, classically canonically conjugate, will make will be anti-commuting. Non-commutative when they are when you move from the classical to quantum mechanics, right? So the simple example is X and P. X and P, right? Gives you unexpected non-commutative. They are classically canonically conjugate. The Poisson bracket of there is X and P is 1, right? So another pair which makes similar is time and energy. Right? And third pair, which is also very famous, is theta and J theta. So, if any one of them matches with these pairs, is correct answer. Right? They are canonically conjugate. Energy and time is canonically conjugate variables. So, if a system is, doesn't depend on time, and its energy is conserved. So, if a system doesn't depend on position or displacement or translation, its momentum is conserved. The system doesn't depend on the angular rotation, its angular momentum is conserved. They are canonically conjugate variables, classically canonically conjugate variables, and quantum mechanically they are non-commutative. And they satisfy Heisenberg's uncertainty principle. So this is so I have discussed these 5 problems today. I will come up with more number of problems in the next lecture. So please do watch this lecture and like and subscribe, comment. If you have any question, please do ask, do write in the comment section. We will look into it and we'll try to address it or help you out at least, right? So these lectures are completely free, so just go through them. Thank you.